Yes, we will
Awesome.
absolutely do a demo. I think what we'll probably do is recreate the I don't even, I've got some, we've published some photos from the DEFCON demo. That's our biggest event of the year, but we didn't actually do a walkthrough of the demo because DEFCON TV interviewed us and did a walkthrough of the demo. And when that comes out, I can then link to it. So I didn't do like a separate video of usually we do for big events at some point, and it's always late in the event, like right because you get there and you're like you figure out your patter or you figure out your summary, your elevator pitch for your demo because we're demo driven here, like the demos are where it's at, and then by the end of the event you've got it down, and that's when you need to go ahead and record it and not on the first day. You just try to figure out it's a little more awkward. So by the end of the event, whether it's 1 or 2 days, then you've got like, yeah, okay, this is, and you draw people through and you know what to say and you've got some phrasing down. And we had that. And but because they had interviewed us at the right time, I didn't go ahead and do that. So yes, I think what we'll do is, and now it's already stale because the two big sections of that demo are now connected or starting to connect. And if you've ever done any sort of like auto mechanics work, like working with engines and stuff, when you do an engine rebuild or restoration, and the first time that you actually get it to catch and fire, and it's got, and it might die, or do something weird. And so we're at that stage. So we actually have end-to-end demo for, from the microphone to the airwaves for the uplink for the satellite, and for terrestrial simple repeaters. That's it. We've got the end to end for that. That's that's it. That's the essential part. So we knew that this would work, but the actual implementation is important, and separating the two was the right idea. So this big step is getting all of that working. The part that's now the short straw is the part that used to be the long straw in the when you have straws, right? So the the receiver on the satellite. So this is based on Theseus Core's open source multi-rate or work. So a multi-rate processor or polyphase channelizer is basically what it is. So it's really good work, originally done in GNU Radio for RF knock deployment, and we took that code base because it's very well done, and then adapted it to our use. So we got this working and demonstrated, and it was like, oh, okay, the receiver is starting to emerge out of the murk, and well, now that is actually the most immature part of all of this. It's the part that needs the most development because it's ready for, the 80 kilohertz channels. I think we gave it a wide margin, and the documentation for that is essentially one page, of here's all the channels, here's how many channels, here's the rates and everything. And it's deployed on the hardware in the Remote Labs West.
Oh,
So
wow. That's really far along.
that, well, it felt like it, but like it would show up and fire up and then go, oh, look, here's some results. Here's some IQ samples, spew, spew, spew. It's like, okay, well, that's not like, can you get voice and text and stuff out of that? So there's a lot of work that needs to be done there. And there's also a
Mhm.
lot of work on the actual okay, so we have all these FDMA channels, these frequency division multiple access channels, and are all essentially opulent voice channel. And yes, we can receive those and we can turn those into some data. Now, what do you do with it? Do you just simply blindly package it for DVB-S2 frames? Yes, you could. You could just package everything up, and then you've kicked the can down the road for the ground station receiver to sort all out this data, like from all a bunch of stations, like wow. So you're now in the middle of a cocktail party, as we used to say in CDMA work. So the I think there's a lot of work that can be done on the satellite in order to figure this stuff out, and that actually can be also deployed terrestrially as a ground sat or as a full, a big repeater. For a simple repeater like we see on VHF, UHF, where we're pretty much there, and we have a demonstration conference system or a demonstration repeater that's been running since DEFCON, and that's what we use to test in the lab. So it's running on an ORI Linode server, and it's working. So it doesn't do anything like the conference features, like, oh, I have a D&D group, or I have a emergency communications group, or I have a regular, sched with this crowd of folks, for drive time. That stuff's not there yet. It's just a simple repeater. So everybody that connects is also repeated back to everybody that's connected. But wow, that's what you have with your typical amateur repeaters today. So, you know, so more work to expand that, but for a basic demo that worked and worked at DEF CON, which was kind of cool. You know, demonstrations are all and presentations are always exciting, and you should never promise anything. I've learned the way that the advice goes is like, okay, so if you have a demonstration, you get up at the podium or at the table or at the booth and you go, watch this. You don't say anything else because no matter what happens, you say, watch this. And if it works, then you explain. And if it doesn't work, then you go, and here we see part of the process, working perfectly. And then you highlight that. So after hard experience, I think all of us have learned. You just say, "Watch this," and it rips. But for DEF CON, the demonstrations are, which is supposed to highlight like it's not over the air, it's just over the internet. So it's like IRC or IRLP. It's your sort of an amateur, and you go front end, very front end, and you use your browser. You have a microphone and your keyboard and your data files and this is the user interface and the user experience. This is what it looks like, and the particular codec, voice codec, the Opus is working, and that's what you hear back. So we're not adding any sort of problems with links in digital. You would hear this as essentially not hearing it, right? So you don't have it works until it doesn't work. So what you're hearing is the frames passed over the internet. It sort of is a demonstration of what it might sound like if you also had an over-the-air link. Adding in an over-the-air link, some people won't make it through because they will be edge of coverage and it'll drop off pretty suddenly. At some point, the forward error correction will just simply poop out. But up until then, it will sound good. It'll be corrected back to the way and it sounds really good. I guess we keep reminding ourselves of how much better this sounds than ambi codecs, which are in System Fusion, basically all of the different D-Star, all of the commercial options all have the ambi codec, low bitrate codec, and then even the one other open source digital option uses codec 2, and the highest you can get out of codec 2 is a very low bit rate of like 3,400 bits per second. It just sounds really kind of harsh. So hearing 1,600 16,000 bits per second codec is very different. And we do have a sort of an upgrade path to 32 kilobits per second. We could pull it off if we wanted to, but honestly, the voice quality for 16 kilobits per second is outstanding. And having the keyboard chat and data and authentication, authorization, and control all working, like you don't have to switch modes, really is the win that we thought. It just feels better. So all of that's starting to work end to end, which is a big step forward, really. I think that at this point, somebody that was kind of motivated could get the repos. They could put it on their, if you can get a Raspberry Pi 4 or 5, if you can get a Pluto SDR, then you have our radio. That requires a lot of sort of development mindset and experimenter mindset. And more radios doing it would be great. But at this point, somebody that was motivated could get that working and then log into the conference server that we run in all the time that's running, and as long as there's somebody else to talk to, then you can hear what it sounds like.
I just ordered a Raspberry Pi 5, and it looks like the Plutos are a little bit harder to get, like they're on 10-week back order or something. Does that sound about right?
Yeah, Plutos go on back order every now and then. Like there seems to be some sort of oscillation. And honestly, ordering any sort of electronic component right now is kind of tricky with a lot of unknown factors with availability and cost and shipping. So, if you got a Pluto, you're good. And if you can order a Pluto, just go ahead and put in the order. The back orders seem to flush out pretty fast. The right answer is to like continue to make it work because there's issues with the way that it's connected together. The human radio interface is interlocutor that handles usually runs on anything that runs Python. We've targeted the Raspberry Pi 4 or 5 because it's cheap and lightweight and is the sort of thing that you would expect to sort of see with this. But you can run a laptop. Mac OS and Linux are working pretty well. And the instructions for Windows, we still have to sort out some issues with getting it to work cleanly on Windows, but obviously we want it to work on Windows as well. So as long as you have a browser, a microphone, and or a keyboard, microphone's really optional. You can run it in chat only mode. That's not a problem. And with the audio transcriptions working, if you can't make a microphone work for whatever reason, you're still okay. So once you have that, then you're sending the frames to a modem. That modem right now is on the Pluto, but it can also be another computer. So another computer running this software will understand your frames no problem. So you don't have to have the radio link at all. Obviously, we want the radio link and to make this to be a radio system, but there you go. It works, and you can demonstrate it with the conference server that we have. So, okay, now we have the modem, Locutus, running on, running on the Pluto for the first target. We take this HDL and port it, or other people that will go, hey, I think I would like for it to run on a whatever, then they would be interested in deploying it. Okay, so all of that's still sort of at the prototype or off the shelf, cobbled together with duct tape side of things and Python scripts. That's great, but the next step is to then start seriously looking at custom hardware and figuring out where and how we want to manufacture it to where people can just buy a radio and it's all integrated and it works. And also, hey, here we go. We have this better way of communicating that really serves the amateur radio community better. The voice quality is much better. It is much easier to listen to. It's a joy. You can actually recognize the person. You can hear all sorts of things. Not fatiguing to listen to like Ambi or Codec 2. Great. Okay, so got that. Got the integration of the voice and the keyboard chat and all that working. Now, when we come to amateur satellites, then we have some options here. So we're going to present it this autumn to AMSAT DL and to ESA and to JAMSAT. They're interested as well. And so maybe we'll get some interest from payloads that are coming up over the next year or two. And that would be really great because this is what we've been designing it for, and this is where it will really shine and give people a good experience to have amateur open source digital radio communications. So that's where we're at. A big milestone to having end-to-end sort of stuff happen. And yes, I think what I'll do is we'll walk through in the lab and make a video that just focuses a short one, like a couple of minutes long that walks you through from how it's set up to what's happening on the spectrum analyzer to show you where we're at today. And we do have some bugs. So there's things that are not working completely right. It's handling the sessions pretty well. We still have this weird carrier that you get from Pluto SDRs where they stay on, come on when you go through the whole IIO or industrial input and output library that the Pluto SDR uses. A lot of SDRs use, that you get this activity on the transmitter when you're not expecting it, and we need to solve that. When it's off, it needs to be off, and when it's on, it needs to be on. And so those sorts of session ideas need to happen whether or not the connection from the human radio interface is UDP or TCP. So we are going to fix that and make it work as best as we possibly can, and then explain how it's working and show it. So that'll be a separate video. I think probably this meeting is for hashing out the details and reporting and doing roundtables and, how we're doing, what we need. And that we'll make a full-blown demo separate and then spread that link around. And we'll keep doing these demos in the lab because I think we're at the point where they would actually be useful. So I hope that answers the question. All right. So I think if inadvertently given an update on what we were doing, and it didn't mean to do that, but we'll just run with it. And I'm going to hand it over to Paul to talk about all of the things that happened with the remote lab gear and how that was part of this process over the past week. And maybe anything that you have to add about the what we've done, and whether, any plans for the future. So turn it over to you.
Okay. Well, we ran into a little bit of a snag on using the remote lab, and that the VM we wanted to use, uh, Karapi, was almost out of disk space. And that's just kind of a surprise because I haven't really been using it for anything that would consume a lot of disk space. And a quick attempt to scan it for disk utilization. Well, okay, there's more disk space than there was, but there's still a lot of disk space that's unaccounted for. So rather than try to do anything radical with that, at the risk of losing some work there, we brought up the other unit, the other unrated server, which we were going to deploy at the remote lab south, and is now here for experimental purposes. And we have a new VM on there that's got all the disk space in the world, and hopefully will be fast. Well, we haven't reached the point of knowing that for sure yet. It has a dedicated SSD to it, which the other ones did not have, which should, if it's storage bottlenecked, which was my theory, then that problem should be gone. Um, I assume that's what you meant by remote lab going is on, because not much else
Yeah.
went on in the remote lab except we set the stuff back up that had gone to DEFCON and been demonstrated there,
Yeah.
put it
So
back to
I
work
have to
in the remote
defend the
lab.
honor of Remote Lab South because absolutely the disk space has been consumed by a variety of projects, not least of which is a lot of MATLAB work for modeling of a variety of things. So I suspect that repeated deployments of like machine learning models for MATLAB is probably consuming lots of disk space. So it's not for nothing. We do have lots of things going on, and there was some synthetic aperture radar experiments that consumed disk space. And what I do is delete some of this stuff like after it's done and proven. Um, but as we know, servers and um, computers are complicated, and that could be why. So the growing number of projects and the versioning and maybe the handling of versions might be a little naive. So that may be the root cause of the disk space on Remote Lab West. So it's very fortunate that we had a whole other parallel system that we could just deploy, and then go ahead and try to stand up another bit of work here. The other reason that we did this is because of the version of Linux. So the Remote Lab South has what is now an increasingly elderly set of Linux or Ubuntu OSs. So the virtual machines are particular versions, 18, I think, 20 maybe. And more we're seeing some limitations with maintaining that age of an OS. Now, the reason why that we do this is because of the compatibility between a variety of things, like everything from MATLAB to HDL coder, to the way that analog devices has their particular toolboxes, and it's a lot of moving parts. And so when we figure out a recipe, we stay with it until we are shoved off of it. And at this point, we're now being shoved off of it. But instead of having to tear down and redeploy on Remote Lab South, we fortunately have a big computer that we can just move to. And that's what we're talking about here. So we move from keeping Chonk and all of that stuff stable. And then we have stood up the Remote Lab South computer in the lab, which is called Chub. So the disk space was a surprise to Paul, maybe not to me, but like, yeah, okay. So we're using up disk space, and also the OSs that are on the Unraid server are getting a little elderly. Instead of doing all the stuff that you need to it puts you at risk when you upgrade an OS and you break your tool chain. So make before break is the choice here. So that was another factor, is the age of the OSs, and to just kind of move to the current 2022, I think, for the Ubuntu, and 2024.1 for Vivado. So back to you.
Yeah, that's correct. But the scan I did for disk space utilization would have picked up any of those projects that had been used up a lot of space. That when I first started looking at the disk space issue, there was only 9 GB free, which is running pretty close to the edge for a Unix system like this. Um, just rebooting it, it went up to 30. So there were some lost nodes there, and 30 is a usable place to be. But some of the projects that we deploy are bigger than that before we even start working on them. So um, it's not enough to do an arbitrary set of workloads. Um, and there's about another 30 that are unexplained, that are unaccounted for. I did a disk scan of everything that we should be adding large stuff to, basically all the home directories, and haven't found it. There may be something somewhere else, or something corrupted in the file system or something. I don't know. Uh, the longer term solution is to have more space, and that's we have that it's in hand, but not deployed in a way that we can use yet, except on the new server.
It's working good for me. So I think that's great. All right. So I think we've been very transparent about the hardware resources, challenges, updates, upgrades, good news for Opulent Voice. So I'd like to turn it over to Pete, because he has a variety of things, I think, to share with us and questions to ask.
I don't actually think I have much to share today. I mostly came to hear about Opulent Voice.
Okay, cool. Yeah, no, we're pretty happy with this. The way that it's deployed right now, with there's a human radio interface, the interlocutor, which we've been reporting about. That was one of the short straws. It was a place that we did not have anything really working very well. So we spent a lot of focused effort on that. We demonstrated that standalone at DEFCON, and we've demonstrated early versions of it, at events over the past, I'd say, 18 months to 2 years. Since May or so, we've really dialed in on this, and really picked up on the past 2 months. The part that over the past week is a relatively new part. We've had application code running on the Zinc processor in the Pluto SDR for a while. This is what manages the PRBS, or the pseudorandom binary sequence test that constantly runs. That's how we've been showing off the modem, is a PRBS test, with all sorts of, like, okay, you take them further and further apart or block the signal, you can see that we get lots of errors, that sort of stuff. Okay, so, and also PRBS allows us to really focus on modem performance, like make sure that the modem's working well. Matthew Wishick is the lead on that. And we reported last week that it's gotten an award. So it received a ARRL Technical Innovation Award for his work on this, because it's a really nice, clean, modular modem approach, and the pieces are all reusable, and it all kind of goes together, works great, and is very user friendly to kind of deploy to your Pluto. And it does MSK, minimum shift keying, not terribly well covered in open source community until now. So all of these factors were why it got recognized. Matthew says so there's a bug in there. There is something that he doesn't like. And I think Pete worked to kind of figure out if all of the clocks are cooperating, because the strategy that we have for the proportional integral gains on the Costas loops, why did we get such different results in theory on paper that worked in the code? So there's still some things, I think, that need to be cleaned up and fixed. There's some shifting about of parts of the design. Overall, though, it's delivering really good results over the air. Could be perfect, but we're well past the point of it being good enough to share around. And it's been appreciated and used either as a model or used as part of designs by other folks. So getting good traction there with the open source contribution to minimum shift keying. Uh, Minimum MSK is really interesting. So if you're interested in modulations and are familiar with FSK, AM, QPSK, whatever, look into this because it's really pretty neat. It does stuff that at first it's like, oh, that doesn't seem to be possible, but it delivers really good results. The two big wins are that it is uh, the amplitude is it's constant envelope. So you get this constant envelope aspect to it. And you also get a very interesting thing that happens with the spectrum. So the central lobe, where almost, so you have a lump of digital signal, and then you have these little side lobes that go out to infinity. Now, in some cases, with some modulations, those side lobes are you're losing energy there, right? You have to filter your signal. Oh darn, I cut off some of my energy here. We put up with it in digital communications. With MSK though, the way that the math all works out, which is neat, uh, like 99% of the energy is in that central lobe. And at first, you see people claim, oh, you don't even need filtering. Of course, you still need filtering, you do, because the math is promising you 99% in that central node. But like we all know that actual components do strange things to you, and your implementation and algorithm can also do strange things to you. So, you don't get away with like no filtering at all, but your filtering requirements are now very relaxed. It's pretty easy to filter because the vast majority of your energy is in your central lobe. That comes out of the math. So well worth the time to study. But wow, the demodulation, modulation, demodulation, it is different. It's a different sort of approach. So we do our very best to kind of describe it, to lay it out in either the source code or the theory of operation as best as we can. A variation of MSK is the Gaussian minimum shift keying, or GMSK, which you see almost everywhere. And you add sort of a Gaussian filter to straight up MSK. We're just using straight up MSK. But if you add the Gaussian filter, then you get some further advantages because I think the big advantage is that it lets you pack in more channels more closely. So co-channel interference or interchannel interference goes down. But do we need that in an amateur setting? No. So we decided, no, okay, Gaussian filter, we're going to set that aside for right now. We're going to focus on making the MSK really well explained and working. And, we don't have the sort of financial pressure to pack in lots and lots of amateurs into our uplink. We can afford to kind of spread them out a little bit more because there's a trade-off with everything. You add in GMSK, you compact people a little closer, but I think you lose some SNR. So you pay it in signal to noise ratio. With a space application or an amateur application, we really want weak signal to work really well. So this seems like a totally fair trade and you can all add in the Gaussian filter later. That's really something that can be separated out and very modular. So that's kind of the thinking behind why MSK and not GMSK. Occasionally we get asked about this, like, why are you not doing GMSK? Everybody does that in commercial settings. And that's why. Cool. Okay. Anything I forgot, Paul?
Well, you covered all this stuff, but if you want to do a demo, I could show spectrum analyzer results.
That'd be good. Just say, watch this.
Yeah, that'd be pretty much it.
Okay, I will. You got the floor.
Okay, you should be seeing my spectrum analyzer. This is the video capture version of the spectrum analyzer rather than the remote control version.
Okay.
I've already got interlocutor running. I'm going to start the dialogus. You have to type in the password because it's not set up for. So there's their dead carrier that we get when we turn the thing on. It'd be nice if that didn't come up, but that's what we got. It's not modulating yet because nothing's being sent over the encapsulation port. So if I now type in a a short message, which would be 1 frame worth of transmission, followed by a second of hold time. Let's see what happens. So that's close, but not no cigar. I'm being right. Notice it flickered on and off a few times. We don't know why yet. It should be coming on, staying on solid for a second, then dropping off. I'll do that again just for fun, except it won't work because the software crashes after one attempt. So
Yeah.
I'm going to restart it. Notice there's a blurb of energy when I restart it as well. And then another message comes out. Same way, it's blinking on and off. So that's consistent. That'll make it easier to debug once we get a chance to dig into the issue. At one point yesterday, we were to the point where I could actually push to talk on the interlocutor, and you could see it trying for a while before it failed. But that doesn't currently work. So that's where we're sitting at getting all this interface to the modem working. It's showing signs of life.
Yeah, I'd say that's solid signs of life. And then before that version, we did have a push to talk that would stay on, but stay on a lot longer than it should, and then eventually tail off. And we figured out that the frames were all a whole hell of a lot longer than they should have been. So it's basically, if you've ever done this sort of work before, it's totally normal. Everything is proceeding exactly the way that it does during development. But the kind of the key thing from seeing this, if you're seeing things start and stop on a spectrum analyzer based on your input from a browser window or a microphone, then that's getting all the way through. It's being delivered to all of the different parts of the process. And I think that within the next week, we will have substantial improvement. We know what's the problem. We know the problem behind the crashing. We reordered the functions and modified the main program. That's where the problem comes up. It's checking for a stop condition, and it's doing exactly what we told it to. So that part should get cleared up, and being able to re-enter the code and do another transmission should work again because it was working before. So it's just the normal sorts of things for this sort of work. It's really nice to see it show up on the spectrum analyzer rather than be two separate projects, integrating two things from that collects things that a human does and then puts them in a form that a modem can understand. That's not terribly easy. Sounds easy on paper. And when you do a block diagram, it's just one little line on the block diagram. But doing it or actually executing it and getting it to work over the air is not easy. And we're there, and we're going to continue and press forward and involve anybody that wants to work on it. The next big batch of work is going to be the receiver on the satellite. So when we're talking about transmitting, this is a single channel, and we can have a whole system that's a single channel, just like in traditional amateur radio repeaters. We'll do that too. It'll be deployed and demonstrated and given away. But for the satellite or for a very full-featured microwave repeater system on Earth, then we have frequency division, multiple access. We have communication back and forth on the control channel about which frequency you're on for the uplink, but which uplink channels are open, and then the satellite's doing, or ground sat is doing a lot of heavy lifting with, look at all these channels I have and look at all this stuff coming in, and I have to correctly multiplex it and put it onto downlink DVB-S2 frames. So that part, that's now the short straw, so in the before times, in the past, that's actually been the part that was working and demonstrated, and now it needs to be caught up. So there's a lot of really interesting and cool work there that doesn't appear anywhere else in amateur radio. So if you're interested in this sort of work and want to contribute, we got lots of opportunities here and a lot of people willing to collaborate and help.
What sort of bit rate do we envision will be on the satellite downlink once you aggregate all the FDMAs?
Let's see. I think we penciled in up to 96 uplink channels. So we have a 10 megahertz allocation on 10 gig for satellite downlink. This is now when we say allocation, this is not from the FCC. This is sort of the agreement in the community for how the band plan on 10 gigahertz works. But we're like, oh, okay, 10 megahertz, sure, we'll take it. We'll take it all. We'll use that, no problem. So we kind of penciled in a 10 megahertz or up to 10 megahertz downlink, and that would give you, I think, 8 megahertz bit rate given the roll off that we anticipate in DVB-S2. And then there's a little bit of overhead because we're using GSE and not MPEG. So we get back some bit rate there. So yeah, it's good, up to roughly 100 simultaneous uplink channels. Now we can, the demonstrations and initial results on hardware, you can see where it might be less than that. When we did the phase 4B, I think. So the satellite work with the wide field of view launch from the Air Force, we had a potential launch there, and Virginia Tech was the partner to work on that payload. When we went through the whole process, it was not going to be a 10 megahertz downlink. It was more like 1 megabit downlink, which is still substantial. That's still a pretty good thing. So the range of like anticipated deployed prototype to amateur implementations that we're talking about is anywhere from like 1 megabit to 8 megabit downlinks. We could go bigger, especially if we go up in frequency. We have more bit rate, but you also have the obvious challenge with beam width, available hardware, radios that can do 24 gig and 47, now we do have some sketches and we're fully aware of these allocations and plans and all. But for right now, the 5 gigahertz uplink and a 10 gig downlink up to an 8 megabit bit rate, 10 megahertz bandwidth. That's what we're kind of looking at to kind of deploy. So that's what we'll present to the ESA in September. And that's what we're talking to AMSAT DL about is that kind of up to that level to kind of honor the current band plan in 10 gigahertz.
So then with those uplink and downlink user bit rates, do we already have an idea of what a nominal user ground station looks like for uplink and downlink? Like what antenna you need for the couple megabit per second downlink and what you need for the uplink and so on?
Yeah, I think there's existing stations from QO100 that are in the ballpark of what we're talking about. So you could set up another like Pluto SDR that would be your downlink station. So if you go look at like the QO100 the high bandwidth or digital downlink stations, you're going to see like the ballpark of what we're talking about. Yeah, that's a really good question. So I don't have anything more than like sort of a vague yes, off the shelf SDR can do it. That was actually the first thing that we tackled, and we're now looking like 4 or 5 years in the past when we demonstrated downlink stations running DVB-S2. Here's an encoder. Here's some random data. Here's what your ground station looks like running on a B210 or Pluto at GNU Radio conference. So that's basically all we know that's kind of the capability that you would need. And now you would have something very similar to the interlocutor code that provides the UI UX interface running, giving you the presentation of here's all your UI bubbles, here's the conferences that you can join, that sort of thing. So that part coming along, but the ground station hardware for the fully featured, DVB-S2 downlink like HiFi not quite there yet. So those early demos, I think, sort of showed the promise of like, okay, we can handle the bitrate, we can handle the processing, but the user presentation, that's through interlocutor, but that connection to a ground station hardware not really implemented yet. So that's probably the shortest, that's one of the shorter straws right now. So an early demo and sketching out, not the sort of thing that we have been spending time on over the past year or two.
And for the user station, is there an easy way to do the FEC decoding of DVB-S2, between say 1 and 3 or 4 megabits a second? Is
Yeah,
that like an easy thing?
easy in the sense that we did it. Yeah.
Oh, it's done. Cool. Well,
Yeah.
that's pretty good.
Yeah. Yeah, so like the LDPC, all that stuff was slogged through by a number of really amazing volunteers like Sawato. So the interesting thing is that the encoder for LDPC is actually no joke. Usually encoding is simpler than decoding, but for LDPC, it's actually fairly heavy lift, and that code's in a repo and has been demonstrated multiple times and used by a variety of folks. And we also have a C code version from Iman and Iman on it and Aman Inan. I hope I've got the name right. Sorry about that. But he's a volunteer and collaborator and did a C code version, which actually ended up being used in another ORI project. So that all fed into work that helped Ribbit come about. So the like handling the DBBS2 channel protocol, implementing it. We spent a lot of work on that and we got that all to kind of work and understand it fairly well. The adaptive coding and modulation aspect is something we're very comfortable with in terms of the downlink. And what we anticipate is helping maybe weaker stations with more coding and different modulation than the stronger stations. Since you can assign this on a per frame basis in the downlink, we're able to kind of like support a variety of stations. Now, this is different than you have in a broadcast environment where all the stations are kind of controlled in the same hardware, and you don't really have to do much adaptive coding and modulation. You get constant or maybe variable. But we're looking more towards the adaptive coding and modulation in order to accommodate homebrew stations, off-the-shelf stations. If we get we tend to be able to provide you a custom, here it is, for a donation, here's your hardware. So that's a tremendous variety of stations, and the protocol recognizes that and will help you out. So that's kind of where we're going with the ground station to be able to accommodate. You here you go. Here's a one-stop shop thing from us, or buy this and this and this and install that and that and that. Kapow. Or hey, here's the protocol. You want to build your own? We'll help you. Experiment with that. That's a huge learning experience for people. So we want to be able to accommodate all of that through the protocol and the deployment.
And then the disadvantaged users, they'll get a lower bit rate because of the adaptive modulation and coding. So what's their trade-off? Do they just have access to fewer of the FDMA carriers?
The trade-off is you still get your assigned channel. And if you and you have to show, okay, yes, I can hear the downlink. Now, once you have that loop assigned, then the satellite goes, okay, so here's how it is. You're going to get a lot of coding and a simpler modulation. That does lower your bit rate. So the bit rate changes as, based on your situation. And you might be able to do chat only at the very edge instead of live voice. So you might drop back to chat only. That might be the trade-off, that you can't do live voice maybe. But maybe not. I don't know. It might just be, here you go. You can't you can't receive as much, or so that's kind of where it kind of splits is what can you take advantage of, what's your bit rate, and we'll see, because we're getting much closer to being able to kind of deploy this and then introduce impediments or in the lab, what we intend to do is to say, okay, here's all these channels to this FPGA station that is running essentially a high area code. Here's this polyphase channelizer. Some of the stations are really weak and some are very strong. Now let's test our ideas and prove them out and show what happens. And yes, your bit rate would fall, and you would definitely suffer some consequences. Kind of the good side about digital sort of services is that you shouldn't see that much of a difference until you reach your cliff and then nothing. So I think that needs some more attention and thought and to be filled out. I think we have a good gut instinct about how it should go down and what you should experience. And since we have an amateur sort of situation here, we do not have the financial pressure to pack in lots and lots of subscribers and take their money and give them something back. And those sorts of decisions actually do affect the protocol and how it's deployed. I think this is one of the things that really attracts us to this sort of work, is that we come from a commercial background, all of us, and we are used to thinking in terms of packing in lots of subscribers and making money from them. And we're used to our protocols addressing this, everything from DVB-S2 all the way up to 5G, 6G. They all do that because it's a market-based or market-driven protocol development. What we've done here is kind of is taken a little bit of a departure from that. Relieving that pressure lets us explore things that otherwise wouldn't be kind of fully fleshed out in protocol development for digital communications. So in terms of like, where does amateur radio best contribute to modern telecommunications? This is one of those places where it can, to really kind of push forward and formalize some of the ideas when you don't have the financial pressure to pack in lots of subscribers. So over the years, we've made some pretty big steps forward and been able to kind of maybe hack some of the protocols in a way that maybe wasn't fully anticipated or intended by the original writers of like DVB-S2. Now we have the opportunity. Here's our uplink protocol. Here's our decisions on the multiplexing inside the satellite and how we pack the frames into DVB-S2, which gives us a tremendous amount of flexibility. It's a great protocol. All of that coming to kind of fruition here will be a big step forward. It's a way for amateur radio to kind of contribute to digital communications in general.
I sort of have 50 questions, but I'll ask just one more and then be quiet. So if we're doing adaptive modulation encoding on the DVB-S2 downlink, and say we use the 64,800 block length for FEC, so how does that play into latency? Because it seems like our uplink's only maybe 20 kilobits a second. And then if we're allocating 64,800 FEC blocks to disadvantaged user versus advantaged user, is there something there where we might get several seconds of latency or anything crazy we should worry about?
I'd have to go back and look at the encoder. The baseline encoder might be a shorter length default.
Okay.
So I'd have to go back and look. I think that it might be shorter than that. But latency is one of those trade-offs, right? So if you have a weak connect, like if your channel, if your conditions are that your connection is weak, like borderline, and it all boils down to signal to noise ratio. So everything for like adaptive coding and modulation basically just looks at the signal to noise ratio and goes, okay, so we can give you this much, we ride the S&R curve to deliver capacity over the channel. That's the basic decision making here in this loop. And latency comes in. Like that's one of the escape valves that you have. Bit rate is the big one for DVB-S2, right? So, your bit rate it rides these curves. So you're not changing your symbol rate. You're freezing all of that because paying for all the filters and the decisions on like how the signal's constructed, you just keep all that the same. You don't change your bandwidth. You don't do that. Your symbol rate stays the same, but the bits coming through are much more heavily coded, or you have to spend a lot more or a lot less on the actual modulation. Okay, so now that we've changed the bit rate, the only other category that we have left here, since we've said, nope, you don't have to change your hardware, you don't have to have reconfigurable hardware or strange SDR things going on, although we could explore that too, but that's hard. So we freeze that, we vary your bit rate. Now we can do tricks with your latency. Like you brought up the block length for DVB-S2, and there's different lengths there in the standard. So I think we picked the shortest one. We also have like pilot tones and all that stuff turned on. Like we'd make it as easy as possible for the receiver to get your signal and to maintain tracking and all that. So I think I think it's 16,000. I'm risking it by saying it out
Yeah,
loud.
I think that's the short block length. I think so. Yeah.
Yeah, we use the short block length for latency from the get-go. So even if you have a strong booming channel, you get the lowest latency as possible. The longer lengths in DVB-S2 are mainly for like broadcast. So when you don't have to talk back, when there's no latency issue with you watching a movie over satellite TV, then you want to use the longest length possible, but so not have to pay the overhead of starting over a new thing. But we use the shortest because we are a communication system and we want to limit the latency. There is still going to be a latency penalty, and we could play around with that even more for really low mobile, low power, compromised channels. There's compromises and there's damage to the channel coming from everywhere. Your pointing accuracy for your dish or antenna, your temperature, I can't tell you how many times my children have caused issues with my radios. Or your weather. We're talking about bands like 10 gigahertz. Actually, I mean, they do cloud bounce for 10 gig. You're going to get weather affecting you. That's a thing. Like, we could give you a utility function that looks at the weather situation for you, that looks at satellite, from GOES or whatever, and tells you like how much loss you're going to expect from where you are at this point. So we can do those sorts of things as amateurs. This software ability exists for us. So there's lots of compromises on the channel. The pointing is definitely the problem when you're talking about, a degree or two of beam width, right? Essentially for pointing at a thing, and it's wandering around a little bit in the sky already. So, you already have a lot of things going on. And so the adaptive coding and modulation just basically says, you know what, we're going to give you the best possible bit rate that you can get. So it's not one size fits all for you. We're going to just dynamically allocate as most bits as possible. Great. But that still leaves latency on the table to maybe claw something back. So it's just a trade-off, and we have to like make a spreadsheet and look at it to see if that would work. But the shortest block length is what we went with in order to give you the least amount of latency. From a human perspective, latency really matters in voice communications a lot. We can't get away from the latency from the path up to a satellite, especially HEO, GEO. That's significant. We don't want to add any more to that. And the biggest way around that we could come up with was like a voice memo like you have in WhatsApp. So instead of really having live voice, why don't we just package it up as a voice memo so it sort of it gets to you pretty quick, but it's still a voice memo and not live, so that there's not this weird delay. So that's what we've been sort of thinking in terms for a satellite deployment. If it's far enough away to where the latency is already a problem, we don't want to add more to that. And that's why the short block length was the choice.
A lot of the system engineering dates back to the system you were talking about, the wide field of view. And that was a piggyback opportunity. And they were providing us with a very generous power budget to work with. And a lot of the decisions we made were based on that. If we get such a situation where we have a generous power budget, then a lot of that stuff will still be valid. If we end up with little bitty solar panels hanging off of our 6U CubeSat, then we may need to revisit some of these decisions. The one that comes to mind in particular is that our baseline design is that everybody who transmits gets retransmitted, and then the ground station picks and chooses which TDM channels they want to use to make their user experience. So a conference room is just a metadata thing, and the ground station would then grab the individual voice channels it wanted and glue them together as it saw fit. That's wasteful of downlink bandwidth. And if that becomes a problem, if we just don't have enough power in the spacecraft to make that much downlink bandwidth with a reasonable size ground station antenna, then we may have to push more of the smarts back up into the satellite and have it be transmitting only one speaker for each conference room. That sort of trade-off is still open to us, and we haven't been constantly revisiting that because we haven't got a fixed uh, launch opportunity with a fixed set of parameters yet. What we've been saying all along is that whole 10 megahertz, we can do a nice voice system with only like a 3 or 4 watt power amplifier at the ground station and a dish about, what are we saying, 30 inches. It's a little bit bigger than a DirecTV dish, but not huge. And of course, if we're able to score a geostationary payload, then it's just bolted down. Uh, that's looking less likely. So maybe it's got tracking, and then maybe that makes it smaller. And a lot of trade-offs that have to be revisited once the specifics are nailed down. Um, I find that stuff fascinating, and it's some of the more interesting design aspects of the whole at the system level. And there's lots of flexibility and room for more work to be done.
That's definitely true. All right. Any other questions, Pete?
No, I promised number 50 was my last. I'm sticking to it.
Well, thank you so much for not just the questions, but all of the wonderful articles and the future work that I think we're going to try to publish in the next newsletter, and all your excellent questions on Slack. And yeah, very, very appreciated. It makes it all worth it.
If you guys see some on-ramp to help out with, like, especially the payload or the ground station for OPV, the satellite side, that's super interesting. But I'm usually kind of floundering about looking for where I could help or what an on-ramp is. So don't be shy if you think you see one.
Okay, yeah. It's messy work to do this sort of work, and that's just sort of why we have Fridays or documentation days, to try to like deliberately once a week sit down, write stuff down, and really kind of make it easy to have a manual. Installation manuals now exist for like the Opulent Voice stuff. The on ramp for the satellite receiver is not great, because this had multiple leads that have focused solely on making code, and I don't think it's at the same standard as the radio human interface or Matthew's work on the modem design. And I think we're rapidly approaching the point where we'll be able to, so the folks that were working on it for a variety of reasons did not make like a full manual or good onboarding written records. And that's okay. That's actually, in the end of the day, that's the job of the directors, me, that we step up and do it. And this is definitely something that would be up to me to execute and do. So I think we're really close to going back through and say, okay, gathering up the existing documentation that kind of explains and onboards. We have a ton of stuff that is now mostly stale about how to access and use the FPGA stations that are in the remote labs, because of the new, we're looking at updating the OSs and moving past the old Debian or old Ubuntu OSs. That this is a really good opportunity to say, okay, set all that stuff aside. These instructions, especially for Petalinux, may now be stale. Xilinx has said, okay, Petalinux is great, but like for new stuff, you want to use Yocto, which is a simplification and reduction. So the Petalinux layer used Yocto all along. Now they're setting aside Petalinux and telling us to go ahead and use Yocto directly. this is a really good opportunity for us to fully flesh out, like, here's how you develop this stuff. Here's the onboarding for the receiver, for the high variety receiver, for the easiest course, how to use it, how to walk through it. So we do have a lot of really good work here, but you're right. It's not accessible for somebody to just walk up and it's like, where do I get involved? That's probably the most obscure part of what we do, you know.
So like one opportunity might be, especially if it's signal processing blocks or whatever, you could just point one out and be like, hey, this, needs a document. And if there's sort of a guideline of what that would look like, I could try to write one for that basic block. And then I'd be learning something while maybe helping fight our way into, where we are. Because I mean, that forces me to go look at the code and learn about it enough to write something. And then that allows you guys to see whether or not I was able to fight my way into it.
Okay. No, that's fair. I think that's good. I'll go back and look at the take this job from the newsletter. It's where we try to put like noted like here, help. Help. Here's some,
Yeah, I'm
well,
not sure. Like maybe I need a little bit of help picking which one, but I'm saying I'm a willing volunteer and I'm defective as an engineer and that I like documentation, so I could write some of that even if I didn't write the code, and that's like all good. So don't be shy.
okay. No, I think time is now to revisit the communications part on how this stuff's communicated out to make it to where you can collaborate. Um, it's never going to be as straightforward or as easy as we want. My feeling is that, gosh, I wish it was. I just want it to be a delight to work for us with us. You know, like I want it to be truly delightful. It's then creating all the documentation to get that to happen is difficult. It's a challenge to kind of figure out exactly what does a technical volunteer really need. And a lot of the times it's clear
Easton said.
like a conversation, it's just a in-person conversation or a set of meetings, or like these meetings really help a lot. Like once we started doing these things, started moving
Easton's next door.
A lot faster. And so it's a constant kind of like balance between so if you sit down and document everything out, you can spend almost all your free time, all of your work time documenting things, assuming, projecting what you would need as a volunteer, or you could go work on the code. And a lot of times people will choose to go work on the source code and to produce source code, and only they know how to run it or what the problems are. And you'll get a minimal set of, so it's you can have the extremes, and any organization of any size has these problems in it, especially volunteer organizations, trying to get involved with a club, trying to show up and volunteer with any sort of charity or join a sports team or league, And so we always need to do a better job. And I think that we've done a decent job because of the documentation days and like repeatedly coming back and going over the documentation every Friday. So I'm going to take what you've said and put my back into it and make sure that we have these things specified for the satellite part, because there was a lot of good work done 4 years ago, and now it's the short straw, and we really need a lot of help here. It cannot be done. It can't be done without a broader technical core of people, and those technical people are not going to be involved if they can't see what to do. So we need to communicate what needs to be done and where you can fit in, and where you can lift up the parts. Where those parts can't be invisible, and you also have folks helping. So I'm going to take what you've said to heart and do the very best I can.
Well, it's actually it's a great organization. I think it's run really great. I'm just sort of looking for what's a loose thread I can understand and do something that then like I don't find out after I looked into it. It's like, oh, we already have an FEC coder, So there's a little bit of that. It's just kind of finding. And I think the way to do it is just find one block that you think might be down my alley, and then just say, hey, how about this? And then we'll take a swing at it and find out if it goes or not.
Okay. No, that sounds good, and I'll do my very best. And if I if we're falling short in this sort of aspect of the communicating the work and trying to connect up volunteers with the work, then please say so. Um, we've developed a pretty thick skin for this sort of. We need to know because what's obvious to you, after presenting or talking about or publishing the stuff a lot and nearly getting it launched in the past, it's really easy to fall into the habit of thinking that, oh, everybody already knows X, Y, Z. And everyone might already know X, but the Y and Z are not clear, and it's easy to kind of assume that, oh, everybody knows this already because I've repeated it like 90 times. And no, that's not the case. When you're communicating complicated subjects, you need to say everything repeatedly over and over again and make sure that it's findable. And I don't think that a lot of the stuff about Hypharia, like that's very findable. I don't, it's in the repo, sure, but I can point you to repo and like, um, I wouldn't want to just read a block of VHDL. Like, great, I can't extract what this really means or how important it is, how significant it is just from the source code. That's never really want to hear that as a volunteer or worker and don't want to ever tell that to somebody. We have 72 repos now. A new volunteer is absolutely not going to be able to sit down and read through 72 repositories of some of it's simple code and some of it is absolutely not. That's not reasonable to expect somebody to just show up, consume it all, and then immediately understand where they can contribute. So, it's a trade-off, right?
A lot of the HDL isn't too bad. I mean, the stuff Matthew wrote, I find really pretty easy to write. So, I mean, there's some of it, at least I haven't looked at all the repos, but some of them are pretty darn great to read. As someone who doesn't know anything, who just showed up, the KISS stuff's really, it's great to read.
Oh, good. You've made me feel great to hear that because we try really hard to make it, especially Matthew. He was like, it needs to be modular, accessible, readable, understandable. We still have lots of things that could be improved. The theory of operation for each individual module really needs to be fleshed out and brought up to standard. But we have tried really hard to make it explained and all that. So we'll
And that's
just
to say nothing of the 3D effects in his ASCII art he writes in the code. I don't know if everyone does that at ORI, but his has some pretty spectacular ASCII art.
yeah, he found a neat it's actually an open source project of in and of itself. So you type what you want the banner to be and it does it. And it was like, oh, that's neat. So yeah, it's gotten a little more popular here at ORI. We use it for in a variety of places. So yeah, it's neat. Yeah, thank you so much for the feedback, and I view it as it's positive to hear that it's parts of what we do are accessible, understandable to somebody walking up, and that yes, I think it's a truism. We need to always improve how we onboard people and make this work useful for them to where you can get professional and personal development out of open source through what we do. You can contribute to something that is meaningful to communications and to especially amateur communications, and that it will be of enduring benefit. So that's what drives us and makes it easy to do this work. But then when it comes to around, like you have to maintain the documentation, you have to actually provide the onboarding, and that's I've taken what you said to heart, and over the next week we'll work on it. All right, I think we're a little over time. I really appreciate everybody hanging out with us today. And what I'll do is we'll kind of close off the normal business meeting, but I want to leave the floor open to Rick to give us any updates on all of the new projects at DSES and anything that we can do in particular for DSES.
Well, I've been working this past week on getting a new set of software running for drift scan work. And well, there's good news and there's bad news. Let's see, can I share? I guess I can. let's see, somewhere here is, there we are. Oh, no, there we are. This is the computer at Haswell that's doing drift scan work. I just wanted to check because we have our new fiber optics installed, but I wasn't sure if the this computer is a Raspberry Pi 5, unlike all the rest of the computers we have there that are regular computers. It's running Linux, and I was just checking to see if it was getting the speed into the internet that the bigger computers are. And yes, we're currently signed up for 75 megabits per second in both directions, and that seems to be working. What I have here is some of my first log files in this new format we're testing, which is part of the Easy Radio Astronomy project. And the good news is the recorded files are in the 100 megabits and less size, and for a day's file, and every day it restarts a new file. That is very useful in comparison with the previous attempt, which was recording IQ raw data files that were in the 20 to 30 gigabit size. So I'm very happy that we're recording useful data in file sizes that are manageable and don't take a whole day to download. The bad news is this is being recorded from a GNU Radio's GRC file, and this is a rather extensive file. You're seeing one corner of it here. There's another piece of it and another piece, and it just goes on and on and on. So I had a conversation yesterday. I've already had to modify this for the hardware we have running, and I talked to the person who's responsible for giving me this GRC file to play with, and I found out that he didn't write it, and in fact, the person who so I added some modules, and the logging module, which is out here, was written this let's see, is that the right one? No. The one down here, Ezra Vector Logger, was written by a gentleman in France in Python. So I was looking at the source code for this block, and the more I learned, the more I realized that most of these blocks were just sort of picked up at random and are not optimized at all for what I'm trying to do. But we're getting useful files, and we have seen post-processing. I was going to show it to you, but I don't have it right now. The post-processing did show that we are recording data that can be processed and show that we receive the galactic centers as we pass by, that the calibration is correct, that we're not showing a galaxy of 10 degrees away from where it really is. No, it's right where it belongs. I have all those charts here somewhere, but I neglected to bring them up. And I don't want to waste your time trying to find them just now. I did say I'd have results this week. Well, we have results. They're very good results, except for one thing. The amplitude of the results, that is, if you look at the data, we have a very low amplitude of actual signals when we pass what are strong galactic signals that should be, for a 60-foot dish, should be much stronger, much more well-defined. And so we tried adjusting the amplitude or the gain of the SDR play module that's out there. And with this set of blocks that should be controlling that module properly, we get nothing. The gain factors change absolutely nothing. We have no idea why. Normally, in the past, we run B210 hardware. Okay, so instead of hundreds of dollars hardware, thousands of dollars hardware, we're not doing that right now because the B210 was considered overkill for drift scan. So I don't know why we can't change the gain. I'm not sure if there's enough signal getting to the front end of the air spy, which is not a sensitive device. So I have a case full of amplifiers and better SDRs and all kinds of things ready to take to Haswell to play with the hardware and see if I can get better results. Unfortunately, we have another science project that conflicts with that. So that let's see, what did Dan say? So he's going down there to look for the Crab pulsar, and he wants to do it at 408 megahertz, which is not hydrogen line. We're looking at 1620 here. And it needs about 2 days of taking my project offline and putting his project online. And then he's going to put the 1620 feed back on. And I think the day he puts it back on, I might drive down there because everybody will be there that I need and try to adjust the hardware. So we're making progress. We can see the hydrogen line of the Milky Way, but it's not what we expected in terms of high performance results. We have a couple of theories about what needs to be done, but anyway, we're making progress. We're getting there.
Yeah, no, it sounds like if you're getting anything out of the receiver, it's great.
We'll
In the
get the
past,
gain adjusted.
yeah, in the past, in GNU radio, the gain numbers in the block, I'm assuming that you're adjusting gain inside of a GNU radio block,
Yeah,
they may not go anywhere. So you need
yeah.
to
So, well,
test out, and
I
that is a
found,
frequent problem with blocks in GNU radio and your radio. So don't trust that the gain numbers do anything or that they do anything at the resolution that you can adjust them. A lot of times there's only two settings. You may have a gain adjustment from 0 to 60, and it only really has two settings. The 0 to 30 is one setting, and the 30 to 60 is another setting. So if you're adjusting, thinking that you're going to see something in the loop, it doesn't work. Another thing that I would tell you very bluntly is that the B210 is absolutely not overkill for this, and you need to not use anything less than something like that. You need to just use the best hardware that you have available and not mess around with something small.
yeah, well, I'm bringing that down with me. one of the things we were trying to experiment with is drivers. Uh, what what blocks actually work with what hardware.
Yeah,
Uh, some hardware like SDR Play is not supported by the default drivers,
right.
so you have to use the SOAPy drivers.
Yep.
And we were
Yeah, we've
very
used
excited.
SOAPy for Pluto, so
Yeah,
familiar.
and I was very excited that the SOAPy driver worked immediately, and but now Dan has a new suggestion. He wants me to put in my better, newer SDR Play module, which is the Duo, which is 2 channels, and feed both channels with the same signal. But that way, he can log on and take one channel and attach it to his set of software, and I can take the other channel and attach it to my set of software simultaneously, in theory, and we can record 2 different data file formats for 2 different purposes at the same time from the same hardware. Now, theoretically, that'll also work with the B210. It has 2 channels also.
Yes, I would suggest just using the B210.
Yeah, well, I can say that uh, that was my idea, but it was suggested to me that I start with the SDR Play. We were going to start with AirSky, but I said, no. SDR Play has a better A to D in it, more bits. And
Yeah.
so we sort of compromised on that. It's just a starting point. We'll keep moving. One of the things that was pointed out is many of the drift scan experiments are being done by hobbyists with 10-foot dishes or even 3-foot dishes. And when you're using a 60-foot dish, your gain is so high and the beam width is so small that even though you say, oh, I've got this 40 dB antenna gain, you're actually looking at a very small amount of noise. So you're not getting 40 dB bigger signals, you're getting higher resolution, not necessarily stronger signals. So I've got to take that into account. And I haven't actually run the math on all that, but I figured, well, I'll just throw some hardware at it. You side note, you mentioned sometimes Plutos are not available.
Sometimes they're off and on.
I
That's
have
just
2
from
of
like
them.
the Mauser or DigiKey. Those are what I'm
Right.
really talking about. You can almost always get one directly from Analog Devices. They'll, if you have an application where you're using it for education, they have usually have a supply ready to go, and they'll give you one.
Oh,
And then
okay.
there's always ones available on eBay.
Well, I have 2. I think one's a Rev A and one's a Rev C. And that's fine because I'm ready to put your firmware in my Plutos one of these days when I have time that I'm not looking at pulsars or something.
Yeah.
And but I also noticed that I bought a couple of knockoffs. I bought a knockoff of a B210 that costs 1/4 of what a real one costs. We've extensively tested it and it performs absolutely as well as the real thing. I've also bought a knockoff of an E310, and there are the same place as knockoffs of Plutos that may actually be better than Plutos because they're in metal cases
Yeah.
and so forth. So
Yep.
uh,
There are options. They're out there. It's just always a changing landscape, and
I'd like to
supply comes
find
and
out. I
goes.
haven't bought the Pluto version yet, but I'd like to find out if the knockoff is at least as good as the real thing. It may you were talking last week about not having loaded the extra parts on the Pluto for the front end. I think the knockoff has all those parts in
Yeah.
it by
Yeah.
default.
Yeah, a lot of them have all the options from I mean, the Pluto is now years old. So it's been
Yeah,
around for a while, and there's a series of revisions with improvements and variations, and a lot of the clones or um, third party sellers have included all of that for you. So it's very similar to the situation that you get with the Hack RF and the PortaPack, that you
yeah,
can get both in one package with a bunch of antennas for a much cheaper price than you would pay for any of the original hardware. So you have the same sort of situation with the Pluto, and the same sort of, as you brought up, the same sort of situation with Etiskir. So there's always, you just need to look around and see, there's variants in third party sellers for anything that has published a schematic. You're going to get something updated, a little more integrated, possibly better performance, or at
yeah.
least the same performance.
I think my Rev A Pluto I got as part of the fee for going to an AMD seminar
Yeah.
on SDRs back in 19 whatever.
Yeah. A lot of times, like the workshops, especially for like RF knock or for anything that Analog Devices was doing, that you would get, if you paid for the workshop, that you would get a Pluto, and you walk away with a Pluto, which is really nice. And they also would give them out to students at conferences. So we several times this worked to kind of get an SDR into people's hands so that they could directly learn. AMD, or sorry, not AMD, I'm sorry, Analog Devices also has a free book that walks you through all digital signal processing from pretty beginner level all the way up to all of the major components. The book was it's free, so free PDF. Really pretty nice. It focuses pretty heavily on the Pluto, of course. So you get a Pluto, you have MATLAB, you're good. Um, and it's 2018
So one
vintage.
of my
Excellent,
one of,
excellent book.
yeah, one of my Plutos right now has a battery pack attached to it and a little bias T, which is powered by the USB port, and a antenna, and it actually talks to satellites. Unfortunately, there's an NDA. I can't say any more than that, but it's a handheld. I can walk around my yard and communicate through satellite, low orbit satellite system,
Mhm.
and it's not the one people normally talk about, but it's
That's
just
one of the
another virtual system.
that's one of the reasons why we kind of targeted the Pluto, is because you can actually package it up, so you can Velcro a Raspberry Pi to it,
Oh
and
yeah, yeah,
have
cool
our
stuff.
system work. So it's not a bad prototyping stage. It's not bad at all. Really super useful, and will be undoubtedly kind of the foundation for the custom hardware that we do. So that's why we picked it, is because people use it for that. We also looked at the Hack RF and the PortaPack, but the thing that's kind of stopped us was the voice codec, the hardware in the PortaPack, and the way that you configure it in software was pretty rough. And
Yeah,
it was that whole sort of the audio path for the PortaPack, which is the user interface. It provides a screen and buttons and headphone jack and speaker jack or whatever for the Hack RF, to kind of turn it into this sort of thing that you're talking about, a portable mobile thing. And it works for like monitoring. So the Hack RF plus the PortaPack works good if you're like doing signal hacking. You want to have a visual, so you want to see what's going on in a portable way. But for audio, it turned out to not be great.
yeah, no, I wouldn't think so. The the unit I have doesn't have the audio and the screen yet, but if I take the battery and this and your software instead of the software that's in it, or firmware, and we add an audio interface, I've already got a package with an antenna and everything, and so we ought to be able to take your protocol, and I ought to be able to stand outside and talk with my handy talkie. It's pretty big.
Yeah.
Sort of
Yeah.
resembles the
Like a, yeah.
1960s
It's like a big
satellite
burrito.
phone.
It's like a burrito size, a big
But,
burrito size. It's
but
yeah,
if I
not
could
like
get
a teeny
that,
little handset, but no, but that's true. You should be able to work, make it
yeah.
work. The
But
the
if I could get that working, I'd be willing to design the circuit boards to make it into something more practical size.
Oh, good. Okay. Yeah, we'll talk. The way that we had it divided up made sense to us and should work for you. If you have your own modem and you have your own modem, it's running in the FPGA. Like you've dropped in the hardware for that. Then all we're doing is feeding your modem with the Dialogus. That's it. So it takes in frames and it says, "Oh, look, it's a legal frame. I'm going to send it off to essentially streaming through DMA to the rest of the chain." That's it. So yes, it does a little bit of protocol checking for Opulent Voice, but if you look at the code, you go, "Oh, this section here, I have my own custom protocol. You could totally change it." So we designed this in a way where it would be adaptable to other situations and it would have a natural division. So in most cases, when you have an FPGA radio block diagram, you are streaming in either IQ samples, in our case bits, and you drop down your, here AXI bus. Now you're getting in the way and you're manipulating the bits in some way, and then you're presenting it, you're modulating it, turning it into IQ samples and out the door. Yeah, that's about how big it would be. That's it
Yeah.
right
And half of it is battery,
there.
and the
Yeah,
other half's a Pluto, and there's
yeah,
the the antenna. This antenna is active, so it needed a bias T. So
right. Yeah. No, that's basically what it is when you lash it all up together. So
yeah.
yeah, I think that's it sounds like we're moving in the same direction. So yeah, if anything that we do is useful, then great. And it's
Well,
published.
fortunately, this commercial project is over. I'm not working on it anymore, so I'm ready to repurpose this thing
Oh, okay,
for
good.
for your project. Yeah, I love it.
Okay, well, we'll just keep talking and keep whacking at it. I mean, the problem is a dumpster fire, and you take a tire iron to it, and you keep whacking at the fire until it goes out, and that's what we're
Yeah.
doing. So
I'm in Colorado. Don't talk to me about
yeah,
fires.
yeah. But hey, Southern California saying
Yeah,
hey yo.
you're trying to compete with us, but I think we're winning something like 150,000
Yeah,
acres in a
yeah.
single
Oh, that
fire.
made the news, man. I hear you.
Oh yeah,
You're,
and it's still burning.
yep. Yeah. Yeah, I hear you.
And
Okay,
that's
well, we'll no, we'll talk a lot more. I think this is
yeah,
the right direction. I think it's a natural sort of division of labor from the different software parts. It's coming together every week, gets a little closer. Very exciting and offers something that doesn't already exist. So we're stoked. And yeah, you just showed something that is exactly where we're at. So it's always really reassuring to know that you're on the right track. And you know
there you go.
yeah, in the end I think custom hardware, where we integrate everything into a nice package, that would be the real nice end. If we ever do is provide really good open source solutions that you go buy this and that, clap it together, there you go, plug in your microphone, keyboard, good. Okay, great. That's fantastic. That's still better than what you got, options now. But having a custom design, like something that you can that's really quite lovely, that's the eventual target here. And we that's what we're aiming towards eventually. First it has to work. Getting there.
Yeah, I'd like to put a mobile radio in my truck,
Yeah, see, that'd be nice, right?
and then I can just talk on the satellites on my 150-mile ride out to Hasbro every now and then.
That'd be pretty groovy.
Yeah, it's much better than talking on cell phones.
Well, yeah, can't compete against cell phones in a lot of ways. And but this is coming right along. So we're happy. We'll keep at it. And I think, let's see. Yeah, next week we'll all be here. So planning on, we do have some travel coming up. I won't be here, so it's going to be up to the rest of the directors to run the meeting if they want to. So for a lot of September, I'll be gone, and for a part of October, showing this stuff and trying to get it involved in some launches, because if we get a launch opportunity firmed up, then that tends to organize all the rest of the work. I find that deadlines like that are very clarifying. So I think we're at the point where some demos start to make sense, and that people start really looking seriously at involving it in launch. And I think that would be very good news. So can't promise anything over the next year, but the steps in communicating to all the organizations you've heard of are happening over the next few months, and we have things to show. So that's the good news. All right, so next week we should meet again, and yes, we're gonna we'll do a video walkthrough of the demo, and we'll spread out the DEFCON TV demo interview as soon as it's published. So I'm watching their channel. So there should be some more visual, like, hey, here it is working. What would be really great is to have not end to end just for the uplink, but end to end for from microphone to speaker on the other side. So that part should work, because all that receiver stuff has been implemented for the reflector, or for the simple conference server. When you go over the air, though, and then you're picked up by the Pluto receive antenna, and then all of that stuff is delivered, it still has to be framed by someone. And that part of the software, not quite there yet. So that part, for a complete end-to-end demo, that and all the way back to a speaker on the other side, that still needs some work. Not as much as before, because a lot of that stuff's already been done. So as soon as Interlocutor sees a frame, it's going to present it to you and do all of the audio and keyboard and all that correctly. But the missing layer is in the receive side, in the application layer on the Zinc. And I think that we'll probably have to decide pretty quickly whether or not the Zinc, the ARM on the Pluto, the 9361, actually has enough room. So we'll do some usage measurements today or tomorrow over the next few days to figure out, now we have the transmitter, can we fit a receiver in there? This really belongs in the FPGA. And Matthew is confident that all of this stuff, that we're demoing and prototyping in the software application layer on the Zinc, actually does, a lot of this belongs in the FPGA. But for now, this is how we're showing the things work, prototyping and software, and then moving it to hardware. So we may actually run out of room on this relatively small ARM. I can't really tell yet whether or not that's a factor. So we'll start looking at usage once we debug the weird things that are happening over the air right now. So that just a heads up that might run into a limit sooner than we think for the software implementation. All right, any other last comments, questions, or concerns before we close for the week? All right, thank you so much, everybody. It could not do ambitious things like this without your support. And for everybody watching, thank you so much for following along and giving us great feedback. And we'll see you next week, and also on Slack.